Hey, welcome back, everyone. So today we're going to talk about SoC, and I'm gonna like basically finish the class in terms of like new material with just giving you a system level perspective, and also gonna give you some background on the topics that is like trending now in computer architecture. And as I said, next week, no class on Monday, obviously, because of the holiday. Wednesday, we're going to still have lots of interesting stuff to share with the paper presentations. I'm going to also give you like a little bit intro after and before each presentation. So I'm going to go actually a little bit deeper for each paper. And then the week after that, on Tuesday, on Monday, sorry, we're going to do a more comprehensive review and a little bit more of like, other newer topics, which are not going to be included in your exam. And then Wednesday going to be the exam, right? So that would be the kind of the remaining schedule of this class. Yeah. So as I said, the goal today is talking about the SoC, the system on chip, and then the newer kind of more trendy version of SoC, which is like chiplet systems. And then later half of the class today, I'm going to talk about the security aspects of SoC and particularly security aspects of chiplets, and that's what my group is quite active in this area as well. So this is kind of like the latest and greatest systems that you're seeing these days on like a consumer grade. So this is I think M1 or M2 Apple chip. As you can see, is like a large part of it is actually GPUs. And then another huge part of it is the memory. Like these are the caches and so on. And then typically, especially on the consumer grade side, on like a mobile or laptop side, you have different types of cores. This is originally termed as like big little. But different companies have different names for it. For example, Apple called them high performance cores and then efficiency cores. The difference between them is the high performance cores are more performant, obviously, but they're more power hungry. And then efficiency cores are lower energy, more power efficient, but lower in terms of performance. What are the differences? You are now kind of expert in this domain. So the difference, for example, with the performance, and actually, let me see. What do you think was the big difference between the performance and the low efficiency? What if you were the designer? What would you change in these two systems? Yeah.
Clock speed, maybe?
Clock speed, that could be one thing for sure. Anything else? Architecture-wise? Yeah.
In order versus out of order?
In order versus out of order, yes. I mean, we don't want to go that low, but yes, definitely you can have like a really, really efficient core that is like an in-order core. Yeah.
Like branch prediction like complexity.
Yeah, the branch predictor could be simpler, for example, than these guys. Yeah. Anything else? Yeah.
Make lower the VDD.
Lower the VDD, okay. Yeah.
Smaller cache.
Smaller cache. Yeah, it's actually like if you look, this one is 12 megabytes and this one's 4 megabytes. Anything else? What about like a back and front end, like the things that you design in your, like think about your CA2. If you want to make it more efficient, what would you do?
If you issue it or something.
Yeah, issue width would reduce, right? The number of functional units reduce, the number of registers reduce, the number of broadcasting reduce, right? So all of those things, right? So that's the main difference between an efficient core and the performance core. And of course, I think the first thing that someone says is the clock and the voltage. These are the main thing. So the way it works is that you make this efficiency cores kind of on all the time. And the first thing that, for example, your system is responding to is handled by the efficiency cores. But then if like workloads, like bigger workload needed, then it kind of wakes up the performance core and then offload things to the performance core. So especially for like mobiles and all, once I touch my screen, The one that is responding to my screen is the efficiency core. But then if I like open like a big application, like I started gaming, then of course everything will be loaded into my performance cores. And then as you can see, there's also other components, right? So for example, this Mac laptops has an 8-core GPU as well. And then another thing that these days is fairly standard is what they call NPUs, neural processing units, neural engine that is like designed to do specific things such as machine learning based tasks, matrix multiplication, filtering, signal processing, video processing, audio processing, and stuff like that. So that's kind of the story. And then, of course, like a lot of computer architecture these days is about designing these two aspects that we didn't touch much upon, on it. The reason is that there's like a separate course for this, and there's another separate course for that here at UCLA. So you should, if you're interested in this, you have already taken those courses, or at some point, I think you should take them. If I like show you a simpler version of that, this is kind of like what you see in a regular system on chip. The reason it's called SoC is that in the past this was um, um, separate chips, and then kind of like it was a discrete based system. And like you have your core, you had your memory, you had your like this chip module like video encoder, audio encoder, and all that. And then you design a PCB, and then you kind of solder these things, and then you connect them. You still like do this in more bigger fashion, but these days all of these things typically goes into the same chip. We can actually integrate a lot of things into the same chip, and that gives us significantly faster communication speed, much more efficient in terms of power efficiency and all that, because on-chip communication and transfer is more efficient. Well, generally, this SoCs, you can think about it as bunch of like cores and some L1 caches. L1 caches usually within the same, chip within the same like design of the core. And this is, by the way, it's the SoC of RISC-V. This is called ChipYard. This is actually an open source SoC that you can build all of these kind of units and then build the whole system if you want to. You can have so these terminologies that you're seeing in this slides are all RISC-V terminologies. You don't necessarily see the same terminology in other designs. So for example, you can have a tile, something like a rocket tile. Rocket is the in-order core, similar to the boom core that we discussed in the class. But this is a simpler in-order core that has a rocket core. You can have actually the boom core here, so you can have a boom tile. Usually, as I said, you have an L1 cache and L1 data. You also want to have a page table and a logic for the page table, so you need to have a page table walker. Then this thing needs to go through connection with the rest of the system. The whole thing about an SoC or generally a big system is you need a communication protocol so to be able to send things and receive things. In order to make this a standard, usually you follow some protocols, and everything is a packet, okay? So you design some form of a packet, you have a header, you send this packet, you receive this packet, and so on and so forth. Similar to the way that, for example, your computer networks and networks in like a big system, like an internet works. Of course, this is less overhead and much less like, you need less metadata because this is within the chip. So you don't need to have like IP and all those other things. You also don't need to check like encryption, decryption, and those things. You don't need the like a TLS layer that you have for the computer networks. But it still follows some specific patterns. I think some of you have worked with like things like I2 or SPI, PCIe, things like that. So these are all examples of these buses. So you can have like usually with these buses has some internal bus that like everybody basically talk to each other and like put things in this kind of a queue. But then this is usually connected to like a more bigger system bus, okay? And this bus is basically connect everything together. So the system bus is the main bus of the system. Then you have other components in the system. So for example, you have your L2 caches and then your DRAM channels and all that. They also connected to the system bus. Typically, since you have multiple channels and multiple components for in your main memory, you might also have like a memory bus, or you can have like a periphery bus. So usually there are secondary buses that you need to have in your system. The periphery bus is basically, as the name suggests, it'll help you with peripherals. Each system usually have many peripherals. Also, depending on the application. For example, if again, this is a mobile application or IoT application, you need to have a lot of these periphery bus because these are the systems that have like lots of sensors and actuators and so on. Versus maybe a server does not need to have many periphery buses, right? You just need to probably have like a very fast connection to the memory and maybe a very fast connection to your GPU, and that's it. You don't need to have like an I2C, or you don't need to like connect the camera or whatever to it. Okay. And then the important thing is that you can have two types of accelerators in this design. You can have what we call tightly integrated accelerators. In RISC-V language, they call it ROCC. Is Rocket Custom a coprocessor, I think it's called. And essentially, as you can see, and then the other option is like you can have like an MMIO accelerator. The difference, this is called loosely integrated or loosely coupled. The difference between a closely or tightly integrated and loosely integrated is that, as you can see here, this is like actually directly connected to the CPU. So basically, you can think about this as like kind of the same unit as the CPU. So within the pipeline, you can actually like offload things to the ROCC and receive things from the ROCC. So that's why it's like tightly coupled. But then many of the things you don't need a tightly coupled integration because tightly coupled is very expensive, right? There are a lot of pins that needs to go in and out. For example, if you have, let's say, a big kernel that, let's say you want to multiply a big matrix matrix multiplication, you don't need this like you don't need to like read things one by one and offload it here. You can say, okay, here's the big chunk, right? So we call it a kernel. So we create a kernel saying that, okay, this is one array, this is another array, and these two arrays are massive. You offload these two arrays to this accelerator and say, okay, go and multiply this. Whenever you're done, send me back the results. Okay. So essentially, this is kind of like goes through the system bus, offloaded here, goes back here. Of course, you're paying the penalty of this communication, but this computation is much larger than this communication is basically nothing. So it's like within 1% or even less, right? So that's usually how you architect these things. Questions here? Cool. So as I said, there's like various IOs. Generally, this is like everything beyond the CPU is referred to as input and output. Typically for memory, we like distinguish memory from IO and say memory is memory, but then everything else is technically an IO. And then, as I said, the number of IOs and there are a variety of the IOs that you need. Is depending on the class of application. So PC versus server versus mobile versus embedded, we're expecting different things. And there are broad categories. So you have like secondary or ternary storage systems like disk and flash. There are some they're remodeling the building. So you can have like a network, like a Wi-Fi module or a Bluetooth module or your LTE module. These are essentially another IO to your system. Then there's like interfaces like the keyboard and mouse and so on. And then like older machines probably have things like printers. And then if it's more of an embedded system, like think about your watch, for example, like an Apple Watch, then you will have lots of like sensors and actuators in your system as well. This is kind of like a little bit more detailed structure of your I/O. So your CPU and cache is like usually like connected to each other. Typically, you want to have a dedicated bus to your memory. You don't want your memory bus to be shared with all the other IOs. The reason for it is that memory has to have the priority. So usually you have a separate dedicated bus to your DRAM. But then there is just a unique system bus that everybody else is connected to that. And typically you have a bridge that helps you kind of arbitrate. So all of these are connected to the same bus. This bridge basically says, okay, now this one is active, and so on and so forth. How do you actually create this bus? How do you create these connections? There are various options. This is kind of like the bus architectures that I show you, and this is the most common way that you have an arbiter, and then you have everything basically connected on the same one. The nice thing about this is it reduces the amount of switches that you need because everybody is just connected to the same wire. But then you can, but this is slow, right? So the bandwidth of this is very, very low because, for example, if both of these guys wants to send something, they need to be serialized, right? So this one needs to send first, and then the second one needs to be first send. But if I want to somehow have like a very fast communication, then I usually go with a cross-border setting where everything is connected to everything, or most things are connected to most things. Okay, so a cross-border is actually quite common in many systems that you need high performance, and then you can have some form of a best word or a hybrid version, which we usually use in a network on chip or NOC. The idea of NOC is that you can actually create a network, a similar way that you have like routers and then devices connected to the routers and then routers connected to each other and then devices connected to the next router. You can have the same thing on a chip, right? So you can create a network architecture with the header and then the data and then all the other like things such as like CRC and like error correction and all that in the network on chip as well. And of course, here you want to kind of prioritize what needs to be connected to what. So you can have like dedicated channel between the routers, or you can have more of like a generic router. The nice thing about this one is that it just creates a very scalable design, right? So you can scale this almost arbitrary to any larger system because essentially all you need to do is adding more routers. Again, same way that your internet works, for example, that you have this system of routers. So that's kind of like, just a general connection of these systems. How do we read and write and how do we communicate? There are multiple ways. Many of these components, including the memory and GPU and accelerators, they have dedicated channels and registers. So the CPU basically directly writes into the registers for that to configure them and to send and receive data from them. Okay. This is to ensure that communication is very fast and it's not impacted by the other activities. The problem with this is that this requires pins, like this requires literal pins that goes from the CPU to those, right? And then your CPU has limited pins, right? So pins has some thickness, and then as these chips get smaller and smaller, you cannot really have like many pins. So you cannot have like a dedicated channel to every single thing that you have in your system. As you have learned, for example, DRAM can only do like 64-bit at a time because of this limitation. Okay, but there are things that you can like reserve, right? So again, like for memory, I would love to have a dedicated pin. The second thing that you usually do is, okay, forget about pins and directly writing things to it. Let's have this thing called MMIO or memory mapped IO. You can treat everything as memory. So you can have addresses. And then if you want to write and read from a particular IO, you can actually treat this as an address, right? So for example, you say that, okay, I have a keyboard, and this keyboard, I assign addresses, physical addresses, for example, from 8,000 to let's say 8,100. So all addresses, all physical addresses within this range belongs to the keyboard. So maybe let's say the first four addresses is for some configuration registers, the second four addresses is for like sending a character, and you can have this as many as you want, right? And then if I want to read something from the keyboard, it basically is similar as I'm issuing a load, okay? I essentially need to issue the load to an address in this range, and then I can have like my registers, right? So for example, X1 and then some address here, right? Or if I want to write to this, I can have a store and then do the same, right? How do I know what are those addresses? Because on the application side, you only have virtual addresses, right? So that's where the driver comes into the play, and that's when you're installing a new system, your operating system needs to understand where that device is. So essentially what it does is that it understands that when you have that call to that particular application, it will translate that address to this particular physical address. So this would be basically, there will be a page table and page table entry that whenever it sees that something like this is happening, it goes and then translates it into this address. Yeah.
Does this map to actual physical memory, or is it like an arbitrary layer and then it actually maps to like some register in the keyboard?
Yeah, it's just mapped to some register. So it's mapped to some actually pins in like a literal pins in your motherboard. So for example, like you have a physical memory that starts from 0 and goes all the way to 7000 FFFF or something like that. Like this is in hex. And then the rest of it does not exist, right?
Right.
But these are all your memory mapped IO, right? So from the CPU's perspective, if I write anywhere here, I'm essentially interacting with the actual physical DRAM. But then if I like address something here, this is one of the memory mapped IOs, right? So it could be the keyboard, the mouse, or the GPU or the CPU, and so on and so forth. Even if I have like a dedicated channel, we also still using the memory mapped IO because it's a clean and easy way to do it. The difference is that if I have a dedicated channel, then there is no address translation required. It directly writes it to that address. If I need to do the translation, then I put it in the bus. It goes through the bus. So that's the difference between a memory mapped IO and a direct connection. But both of them are essentially loads and stores. Okay. And then these are usually an important thing about this addresses is that they shouldn't be cached, right? Why? Because this is like data that is received from, let's say, a keyboard. So it's not like a regular page that you want to cache. So typically, you have to make sure that these things are not going to be cached in your L1 and L2 and so on. Although you can have shared memory, for example, between your GPU and CPU, and those things can be cached, right? Because, for example, you want to like continuously send things to the GPU and receive things from the GPU, or like there is some joint variable that you want to both the CPU and the GPU needs to collaborate on. So those things can go into the shared memory space that both of them can write and both of them can access. And those things can be cached easily. Okay? You also will hear, you probably have heard this term called CSR. This is usually called control status register. So almost all of these IOs has this CSRs, and this CSRs basically configure the system. So for example, you want to receive some data with some bandwidth for some data rate, you can actually write things. So this control registers are helping you to kind of, from the CPU side, to interact with the IO as you want, as you wish. Okay. So which protocols do we use? There are different protocols, and probably you have heard these names like PCIe and PCI and SATA and Ethernet. The difference between them is the how fast they are and how much expensive they are in terms of power consumption and area. PCIe is kind of like this is the current standard in most systems. This is the PCI Express version. And then usually like almost all of your high-speed components are connected via PCIe. There is a newer version called CXL. For some of you have heard about this. This is also an open source standard that some big companies are trying to push it. So it's just like you will also see CXL next to this PCIe. But there's still other types of connections such as Ethernet or SATA or old PCI and so on and so forth as well. Another important things on modern systems is DMA. This is called direct memory access. Direct memory access is basically when I have multiple components in my system, like this. If I want to, for example, if this component wants to write things to the memory, there are two options. As I said, most of these devices can only talk to the CPU through this store and load. So if, for example, I have a camera that is streaming data, then essentially I need to issue a lot of loads. And if I want to store this into the memory, then I need to issue stores from the CPU to DRAM. This obviously is very inefficient because this one goes here and then goes here. So maybe a more efficient way is actually if this one can directly talk to the DRAM. Okay. The way that we do this is direct memory access or DMA. So almost all of the modern systems has a DMA here, a DMA controller, that if the IO wants to directly talk, read or write from the memory, it basically configures this DMA and then talks directly to the memory. Okay. And this saves a lot of space and a lot of time to the system. Okay. So usually, like my graphic card has a DMA, my bus bridge has a DMA, particular IOs might have a DMA, and so on and so forth. This allows them to directly talk to the memory without the involvement of the CPU. Of course, the CPU needs to be informed. So usually, in order to configure the DMA, you first send things to the CPU, and CPU configure the CSRs of these DMAs. But then that's a one-time thing. Afterwards, then they can talk to each other the normal way. And how does it DMA works is that think about this is that this is like a regular store board and load board. So you understand the language of the memory. So you issue the addresses and so on. And then CPU just needs to be informed that, okay, these sequence of addresses or this range of addresses now belongs, for example, to this new device. So if you want to actually go and grab data from it, here's your new sequence of addresses and so on. Okay. Any questions so far? Okay. Another thing that I said is most systems has this network on chips. The network on chip you can think about is that like it's network of routers that have some outgoing arrows that's kind of like some incoming traffic and outgoing traffic. Each of these components in your system has some sort of a network interface that can directly talk to these routers, and these routers can talk to each other, so they can send packets. So, for example, like if SRAM wants to send something to the core through this network interface, they send it to this router. Then there's this routing algorithm that is actually a big part of any of network on chip designs. For example, many of them are just simple as in like east-south kind of mapping, which means that everybody just either send it east or send it south. And then this way, for example, this one send it this way, this one send it this way, and this one receive the data. Nice thing about this is that then you can scale this as much. So if tomorrow I want to add 4 more cores to the system, all I need to do is adding 4 more routers, and then boom, I have my system. There's a whole bunch of problems with NOCs, including like, how do I make sure the routing is the most efficient? How do I make sure that this thing is fair? For example, if this one is sending like many packets, it's going to flood this network and everybody else cannot talk to each other. So how do I make sure the fairness is there? Another big problem with routing is deadlocks. That is like, if I cannot send this information there and this one's kind of stays this here forever, or if we create some form of a loop, how do we break these deadlocks and so on and so forth? So there are a whole bunch of research on network on chips. It was a very popular topic a few years back, but then it becomes again a very interesting topic because of the chiplets, and I'm going to talk about it later soon. What is happening within each router? Router usually has this kind of buffers. That these buffers are essentially just like a group of decoders and multiplexers, and a bunch of these queues. And then these queues are basically receive this data from all of these different directions. Usually a router has an east and south and north and west inputs. So you technically just need to have an input that can basically reserve this spaces. And then you can have some form of a crossbar connection that basically connects all of them to each other. Such that, for example, if this one wants to send from this side, send it to the right. So it's coming from east and coming from south and needs to be connected to the east and so on. And you need a buffer to be able to buffer this for some time. Otherwise, you're going to miss the packet, right? Because there might be other requests that needs to be also routed. So you need to be able to do this very, very quickly. And these are just generic processing elements. It could be a memory, could be core, could be IO, could be a combination of them. Each router might be even connected to a bunch of these PEs. Okay. As I said, the challenges is like performance optimization, scalability, energy efficiency. Security is actually an interesting topic in network on chips these days. There are tons of attacks and papers on similar problem that we had for caches and memory where we have contention. People have shown that, for example, contention in the network on chip can be also extracted as a side channel. So if, for example, one core is sending a lot of packets, the other ones is going to experience some delay, and they can measure this delay as a method to kind of understand the leakage. And as I'm going to talk about later, this emerging computing paradigms like chiplets is actually making this problem more challenging. And then the design ingredients are like the topology, the protocols, routing logic, routing design, etc., etc. So that's kind of like the NOC kind of part of the word. Any questions here? Okay. Last thing is the accelerator design and GPU. As I said, you can either have a tightly integrated accelerator. This is again in the terminology of RISC-V and chippier. So you can have something that can basically directly communicate with your boom core. So for example, if once you have like an instruction that's being decoded, then it can be actually offloaded to the accelerator. So same way that we have the front end and back end, you can actually have the back end as the accelerator. So you don't need to like put it into the scheduling queue and go to the functional units. You can actually forward it to the accelerator and let the accelerator do the computation for you. Okay. If you, for example, also need things such as address translation, you can also query directly the page table. You can directly update your caches and all that. So this is actually why this is kind of, you can think about this as part of your core design. But the nice thing is that you can actually distinguish these two from each other. And then if in future you want to change your functional units and make a better accelerator, you can do that. Okay. Then you will have your MMIO accelerator, and then the way that you can read and write from this is the memory mapping that I described. Usually there are control status registers here that the CPU can basically program, and then this can usually also have DMA access to the main memory, so you can directly talk to the memory as well. There are actually open source accelerators like NVDLA for the NVIDIA that you can actually also play with in this system if you want to. All right. Any questions here? Yeah.
So why would you use MMIO over DMA if DMA offloads the CPU?
So there are two. So the MMIO is for connection between the CPU and the device. So for example, if from the CPU I want to receive a command or send a command, how do I do that? I issue a load or a store with that particular address. That is what we mean by MMIO.
And you can't use DMA in that?
DMA is for copying data. So DMA is not for sending and receiving commands because it's very inefficient. Because DMA, think about it as more of like it's think about it as a task that say, okay, from here to here, copy these things from here to here to here to here, and then you let it be to kind of do that for you. Okay. DMA itself is an MMIO, so everything is MMIO. So MMIO is just generally a way that we can communicate with the rest of the system with the language that we know. Because imagine that, for example, if you want to talk to your keyboard, then you would need another instruction. So instead of a load, you have to like load keyboard or whatever. So I need to create a custom instruction for talking to keyboard. Then I would have need another custom instruction to talk to the mouse, and then another custom instruction to something else. And then if I wanted to add another completely new IO, then I needed to kind of change the processor architecture, which is not useful, right? So the trick is that treat everything as memory addresses, and all you need to do is just add new addresses. And as long as you have enough space in the address space, which we usually have, because address space is 64 bits, and you usually don't fill it, like usually only 48 or 32 is filled, you can add almost any new component to your system. Yeah.
What's the difference between MMIO and like the periphery bus? Like can you argue that like the UART and the GPIO are also MMIO?
There are also MMI, exactly. So there are just different address ranges. This is MMI accelerator. So it means that the accelerator is also, so this is a neural engine. So this one can do matrix multiplication or filtering, like FIR filtering, very quickly. But everything that you see in this picture, think about this way, that if this core wants to talk to this unit, this is basically an address for the core. That's all. So this is one address, this is a different address, different address, different address, and so on. So right. So and then how do we know these addresses? This is where the driver and the operating system comes into the play. Okay. All right. So what's happening now? Like what is the current trends and the future trends? So one important thing is that, of course, we are driven by this thing called Moore's law, right? That for many years, we managed to double the number of transistors and move from one technology to another technology, and we build bigger and better systems. So like you have, a long time ago, we used to have, 120 nanometer, 65, 40, 28, 22, 16, 10, 7, 5, and so on and so forth. This is our kind of latest and greatest. I think if you buy like a M Pro something, it's like 3 nanometer, right? But many of the computers that you have or systems that you have is still in the 7 and 10 nanometer. There are a lot of discussions on how far can we go here, right? So can we go to 3 and then 1? The problem is that essentially like the width of a one silicon atom is like about 0.1 nanometer, like 10 angstrom. Which means that you literally, if you go smaller than that, you cannot even fit one atom in that channel. So there's like a physical limitation at some point that you're going to hit very soon. So the question is that, okay, what should we do? And how we can actually make these transistors smaller and smaller? Because in this industry, in order to move forward and create a new generation, you need to somehow make things faster. Otherwise, what's the point of buying a new computer, right? If your new computer is as fast or as slow as the previous computer, you just buy the previous one. Or maybe after 4 or 5 years, if it's aging, you just let's replace it with the same one, right? So in order for people to kind of buy new things, you need to make things faster. But unfortunately, that seems to be a big problem. I think some of you were in the talk on Monday from Intel guy. They were also talking about this similar things. So the question is, okay, what can we do? There are different ways, people thinking about different technologies, different ways to build transistors and all that. But then the biggest problem that we are facing is the cost. Okay, so this figure here is showing you the cost of the design from higher technology, older technology to newer technology. And as you can see, the cost of adaptation of a new technology when it was 65 nanometer, like if I want to build a new, like I have a foundry, I want to switch to the next node. In the past, it was in order of like 20, 30 millions. But now it's like a new technology is like 500 million. And that's why there's right now, it's only one company that can do this, and that's TSMC. Everybody else is basically cannot do anything because of this huge cost and very, very sophisticated technology that nobody has. And if you actually look into kind of this is a breakdown of where is that cost coming from? And you can see that it's the cost of verification, for example, is growing. The cost of the software development for new EDA tools and new design tools is growing. And then generally, like you see, everything is kind of like growing, but this basically eats up the entire thing. Okay, so that means that this idea of like packing more transistors into the same chip is not sustainable anymore. Okay, so the SoC in the way that we think about it is kind of dying. You cannot like put everything into a single chip. So what we can do instead, this is the idea of what we call chiplets. The idea of chiplets is going back to basically what we had before. Remember I told you that back in the day, we had smaller chips, and then we had like this PCB, and then we kind of connected these chips. together. But then we realized that, okay, we actually can integrate this in much bigger chip, and then basically we're gonna have a system on chip. The reason that we moved from here to here was that this was significantly more power efficient. And then I can actually pack more things and much faster. But then the idea is that if I can somehow learn how to package this, that is, the connection between the chips is almost like this is in a system on chip, then I'm back in business, right? Because now I can then build each of these chips separately. But then I have this very sophisticated advanced packaging mechanism that instead of like having an old PCB, kind of like you have soldering and all, I can somehow put this into some form of a silicon layer or silicon interposer. And then the connection between the chips would be instant. It would be as same as they were on this SoC. So this is where the industry is at right now. Okay, that the big breakthrough is not designing the chips anymore, but how do you connect them in a big system, and how to make sure that this connection is fast and reliable, as good as an SoC based connection. Okay, so this is why I call chiplets. That it used to be big chip, but now it's like smaller chips. So that's why it's a chiplet-based system. The nice thing about this is that this no longer needs to be huge, right? So you can have like a chiplet for your one core of your CPU or multiple core of your CPU. You can have another chiplet for your memory. You can have a chiplet for your GPU and so on and so forth. And then you can make any of those very large. So what used to be all of them one chip, so now I can have as big as of what we used to have for the GPU. So I can have a massive GPU now, but then I can then connect these massive GPUs to each other. Okay. This is actually so the rest of it is I'm going to talk about, borrowed from a good friend of mine, Boris. So it's actually, this is the Blackwell GPU. This is the latest and greatest from NVIDIA. It's like, was out this year. This is actually a chiplet-based system. So this is like, so what these people at NVIDIA found out is that, okay, I can no longer like make the GPU bigger. So what can I do? I put two GPUs, and then I somehow connect them just using this very fast connection, right? And next time, for the next generation, it's going to be 4 of these, or it's going to be 8 of these, okay? So so the way that this works is that now I put this, and then I find a way of connecting this and package this such that it's like very, very fast. As you can see, it's like now it's 92 billion transistors. It's massive in terms of size. So it's like 750 millimeter squared. You cannot put this in one single chip, because generally, if I make a big chip, the biggest issue is defect. Because, like, for example, if I make a big thing, if only a tiny particle like lands on this chip, almost the entire thing might be broken. And if I increase this area, the opportunity for these defects increase with a factor of 2, right? But then if I make this smaller chiplets, build them separately, then the opportunity for this one to be failed versus this one to be failed is much less, right? Worst case scenario, this one will be failed. I just throw this one out. I still have lots of other working chiplets, okay? So the cost of designing this is significantly better and more efficient than that big one, okay? But how do I connect them to each other? I connect them using this technology called interposer, or there are other technologies I'm going to show you in the next few slides. But essentially, the idea is that I build my chip, and then I actually put them into another layer of silicon, and I kind of like then make the wires into the silicon. That's why I have very, very fast connection, because this is similar as an SoC. Okay, and the connection here and here is also similar as an SoC, because this is a 2-layer of silicon that connect each other. So this is not like a bumpers that you have in your PCB, which are very, very slow. Because the reason that like connections are slow is that if there is a huge capacitance, and huge capacitance happens if you have big, holes or big wires. So this is like nanometer scale or micrometer scale. They call it usually pitch. So like the width of the wire. And when the width of the wire is so small, then their capacitance and resistance are very small. So then you can have like very, very high and fast switching communication between them. I actually have some nice figures here. So there is like, this is like, your kind of interposer layer in the substrate. And then this is kind of what we call a fine pitch, because your pitch, your wire communication is very, very small. Interesting thing is that now you can also do 3D, right? So you can actually put things on top of each other and then connect it wireless. So you can actually kind of like go into the 2D direction, and you can also go into the 3D direction. And this way you can actually have faster communication, because when you have 3D, you also have very fast communication between this layer and this layer and this layer and this layer. So it's even faster than going through this way if you go this way. And then you can, for example, have something like, if you have a GPU here and a CPU here and a memory here, then they have a massive bandwidth and a massive speeds to talk to each other. We still can't build this because of the power, because of the temperature. Because if I put a GPU here and a CPU here, it's the amount of heat that this is going to generate. It's so massive that I cannot have the heat transfer to the heat goes out. Because in the past, I have like a big GPU and then I put a very big heat sink on top of it, and then I can like cool it down. But if I sandwich this between two other layers, heat has no other way to go out. So that's the main bottleneck of we are not being able to still build like this very high performance 3D models yet. But there are a lot of people working on this, and you guys probably join companies that work massively on this. Any questions here? Yeah.
Well, what is meant by scale down with the chiplet design, as mentioned earlier? The scaling down is just like increasing the area, right?
Yes. So scale down means this, right? So you want to scale down. So it means that you want to make the transistor smaller, but you want to also scale out, which means that I want to have many of these chips next to each other.
Okay.
So the idea is that if I cannot like make one chip bigger, then I can have many chips and connect them to each other, right? And this is the idea of like, this is actually where the industry is going right now, right? But with this is both scale down and scale out. Scaling down means that it's using smaller technologies, but then scale out means that it's adding more. There's actually these companies like Cerebrus and all, they have this notion of what they call wafer scale computing, that instead of like having like, having smaller chips, like build a big wafer and put all the, chips on that wafer. So that you have, instead of like having one GPU, you have 1,000 GPUs, and then they are connected to each other. So you can actually do massive models on just one wafer. So the idea is that very soon, instead of like having this big racks of servers, all of them would be basically just one small. So it's actually recently you're seeing that, for example, NVIDIA is doing that. Yeah.
Is that robust like the process like variation you were talking about before? Because I know you mentioned like one of the reasons why we use chiplets is to avoid like a problem in one of the areas.
So Cerebrus technology is still not the greatest in terms, but you can think about that instead of like, build everything on the same wafer. I can actually, if I somehow figure out a way to build this chiplet separately and then integrate them onto the wafer, then it works, right? So it's actually kind of like what chiplet industry is going toward.
And earlier with the design cost, why was software like the largest?
Software is because EDA technology, they need to spend a lot of time for the verification, because any newer design requires basically more tighter timing analysis and all that, because there's more failures. Since there are more failures, then you need to spend more time. You've worked in the industry? Or you were? Yeah. Can you share your experience? So like what's changed since?
For me, I think the biggest thing in SoC that I've seen lately is like as Xilinx came out with the new Versal chips with their AI. I think that's how their routing is using that, but I haven't. It's hard to get your hands on it right now because all of this is very much like only the big companies get things.
Sure.
So I think, yeah, I mean, you spend a lot of time just kind of dealing with the software, and a lot of software is antiquated. It's all behind the times, and that's probably why they're spending so much time working with software.
You had a question and you had a question? Yeah.
I mean, it's kind of similar question to his, but if the interposers are like made out of the same fabrication like technology, then like you're supposed to like wouldn't it be hard to make a big interposer that can
No, so the interposer, good question. So interposer is only a wire, so there's no active transistors in your interposer.
so it's easier to, I guess, like
It's very easy to build wires and so the reason that you have defect is when you need to go through this like layer by layer thing of like building transistors. But if I want to build wires, I just etch it. So it's like going think about like the actual like ground, like how do you connect things? So you just like dig out the ground, and that's literally how this. You can also grow things, but both of them are still there is like building fine pitch is not easy, and there is defect, but it's significantly less probability than, let's say, I want to build a big chip. Yeah, the
So
question.
the scaling down and scaling out. So scaling down is coming to an end, right?
Yes.
So the industry is gonna only do scaling out. Is that enough?
Technically, yes. Is that enough? Well, it works, right? So it's like kind of like, the semiconductor industry is more of like survival, has been in the last 30 years, but it works well, right? So it's been survive and doing well, right? Like look at NVIDIA, for example, right? So it's just as long as NVIDIA can have the next level, like next generation chip, then they're good, right? And then they think about the problem, like you punt the ball, few more years, and who knows? Maybe in 3 years we can come up with a new silicon, not a non-silicon technology that fixes this problem. Maybe not. At some point it will end, or maybe not. But this actually ending thing has been happened many times over. So, for example, in 2004. So we used to have only single chips in our designs, okay? And Intel has this Pentium 4 design, very famous one, that they built the new one, and they saw that this amount of heat that it's generating is more than a rocket nozzle, like the bottom of a rocket. So they actually that was a huge moment in 2004 or 5. That they basically realized that they can no longer add more chips to their transistors. That basically, and then so what they did was they add another core and they invent the idea of multi-core. And so now essentially we are not really adding more transistors per core, but we are adding more cores. And for a user perspective, you don't notice the difference, right? And the same thing, for example, with accelerators, that we realize that, okay, time has come for like adding more features to the CPU. Like you cannot do better than a particular branch predictor. So what do we do instead? We design GPUs, and now we can actually have completely different architecture for doing things that the CPU cannot. And then we realize that, okay, GPU seems to be ending, then we design our NPUs and so on and so forth. So domain-specific acceleration. So it's can keep on coming. So yeah, seems that it's gonna work for the next 5 to 10 years, but let's see what happens afterwards. Yeah.
So there is a physical limitation of scaling down, but is there a physical limitation to scaling out? Like the different chips, like the length that they interconnect between them or something?
Good question. That's actually what technically no. So there's like I think I have actually a slides here to talk about that. But essentially, if I have many chips, then I have two problems. There is like a short range communication problem that these two nearby chips that are like within few millimeters from each other. But then if I want to build a massive design, I also need like chips that are like far away from this one. How do I connect that? These days, people are thinking about, okay, how do I make this connection? The one that people are really excited about is photonics. So essentially you can, from this guy to connect to this one, instead of like having electrical, you actually translate into waves, and then boom, you have the speed of light to communicate. So, but you need a switch from electrical domain to a light domain and vice versa. For this near field high bandwidth, it doesn't work. But for this larger bandwidth, it works. And it's actually much faster than, think about like the way that, like, for example, Google or OpenAI and these companies right now is training their like large language models, is that it doesn't fit in one GPU. It fits in thousands and thousands of GPUs. So they actually have like literally server racks after server rack, and they have Ethernet connections and all that. Very slow. That's why it takes months and months for them to train a model. But imagine that I can have this massive model and then I have this photonics-based communication. then I can do things very, very fast. So
That also removes like the heat element, right? Or less element.
the heat element would be the heat element is still there, and that's a major because what used to be a big server rack, and then I can have the cooling. Now it's going to go into one chip, so I need to actually come up with much, much more sophisticated cooling systems. So there is like this phase change, like they put other materials that can grab the heat and then change their type of like from solid to liquid, for example, or from liquid to gas. This way you can make them faster.
Are we just using fiber optics for this, or is it something different?
For what?
For
We're here.
components? Yeah.
So there is actually a big field of integrated photonics, which means that you bring the photonics elements into a chip. Yeah, there are different ways that you can do this. There's I'm not an expert in the field, but yeah, there are lots of interesting stuff happening there as well. Any other questions? Cool. Let's have a quick break. I can come back to this and finish this integration. So let's continue.
When I find that stuff.
So yeah, so if you look at actually at the scaling, so the blue curve is showing that like how we can scale the transistors down, the silicon scaling. The red one is showing you the bump. This is like the connections, the pitch. And as you can see, the pitch was kind of like the same because essentially we never look into the packaging. We never changed the package. We just make the transistors smaller, and that was enough for us to like make the system small. But then starting like the chiplet business kind of like somewhere in like in mid 2010, then you can see that the pitch is actually going down, down, down. And then what used to be like in order of hundreds, now you're trying like we are at kind of like a 10 to 50, but then the goal is like getting to 1 micron or below 1 micron pitch soon. And then that will give us then this opportunity of like then connecting these into a piece of silicon and add a bunch of these together. Okay. So what is this kind of chiplet paradigm shift is going to like help you? It's kind of like it's like a Lego based system, right? So you can actually build this smaller chips, and then you can build them to like you can combine them to build a bigger system. So homogeneous, high power, complex system, and high non-recurrent engineering efforts. Now it's changed into heterogeneous system that you can build chiplets in different technologies from different vendors. Then you can combine them together. And then for building a new system, you don't need to start from scratch, because if I want to build a new system in SoC, if I change part of the SoC, I need to be worried about the entire system. But with chiplet, all I can do is that I can update the core, for example. The rest of the system stays the same. I don't need to pay the penalty of engineering the entire system. So essentially the complexity is now very localized, and I can spend a lot of time on designing a new chiplet, but then the other chiplets I can just go and buy. And then if you're a hardware company, for example, you don't need to build everything yourself, or you don't need to design everything yourself. You can buy chiplets from this other places. So the idea is that soon you're going to have something like a chiplet marketplace, the same way that we build software. That you build like, you get this software from this company and that software from the other company and integrate them together. You can do the same with chiplets as well. So there are lots of research on chiplet design. The biggest one is, okay, what is the right size for the chiplet? And if you're thinking about the right size of the chiplet, there's like a few things that you need to be thinking about. There's a mechanical and electrical aspects for this. If the chiplet, so this way is smaller and this way is larger, you need mechanical integrity, right? So if you actually make the chiplets really small, then there is a whole bunch of problems that you're facing. On the other hand, if you make it much bigger size, it also kind of defeats the purpose. Remember, I want to build smaller systems to reduce the defect. If I make like the chiplet smaller and smaller, then I need more connection and more wires. So essentially, it's kind of becomes like a transistor to transistor. Versus if I go like a bigger, it becomes more of like serializer, deserializer that we have already in R. SoCs. Smaller chiplets, of course, has lower defect probability. Higher chiplets, bigger chiplets has higher defect probability. The handling is that, of course, like smaller chiplets need to have tinier components, and again, handling it in terms of mechanical is much more difficult. And then smaller chiplets means that you have less functionality you can pack into the small device, right? So since you're still limited by the size of transistors, you cannot put a lot of functionality in a smaller chiplet. So you kind of like have just basic functionality versus like a big system would be like a big complex system. So kind of like figuring out where is the right balance for this is an interesting question. How do you actually architect this is also another big question. Usually these days you're seeing somewhere between like 50 to 100 millimeters square is the design of a chiplet. To kind of give you an idea, like big SoCs are in order of like 400, 500 millimeters square. So we're like reducing it by a factor of 10. Yeah.
Just I guess a sort of overarching question, when we're thinking about like chiplet size and stuff and just changing the paradigm of how we think about systems, is that affecting our like computer architecture side of it, or is it kind of still the same as it has been?
Now it's like trickle down into everything, right? So for example, for architecture, you can think about, okay, now if I have many chiplets and many caches, for example, what should be my cache replacement policy, or what should be my data storage policy, for example? Or if I have many cores, what's the right strategy to kind of divide the workload? If the communication between the chiplets are high or low, now I need to factor that into my system. For example, now what used to be smaller overhead for like L3 miss now might be higher or might be lower. So there are things like this. The nice thing that is happening is that your bandwidth and like specifically bandwidth to your DRAM is now increasing. So you can actually bring in much more data. So maybe you can now do a lot of things such as improving your locality and all that. So yeah, there is actually tremendous amount of architecture opportunity in this domain. Yeah. Yeah.
Would it improve the security or make it worse?
Actually, I'm gonna after this, I'm gonna talk about the security aspects. Yeah. Good question. Okay. So challenges at the technology level, of course, the chiplet integration, the cost, the fabrication tools. On the methodology side, partitioning, how do we actually deliver power now to the smaller chiplets? How do you synchronize these chiplets together? How do you floor plan? Like where do you put each chiplet? How do you connect them? Where your wires are? How do you design your CAD tools to be able to design this chiplet-based system? So there are a whole bunch of things that needs to be done. On the circuit level, of course, you need to have now different power delivery methods. You have different density designs. You have this IP reuse ecosystem now because of the chiplets. And then, of course, at the architecture we just discussed, arrangement of the chip, like how do you actually even chipletize a design? Like how do you take a monolithic design of an SoC and how do you decide which part should be one chiplet and which part should be another chiplet? How do you actually make this network design and so on? These are the questions. One of the things that is actually happening right now at UCLA particularly is this design called Silicon Interconnect Fabric, or SIF. The idea of SIF is that getting rid of the interposer completely. And the idea is that let's actually have a substrate that is purely silicon so that actually all the wires can directly go into the silicon. So you don't no longer need like a package and the silicon interposer. Excuse me. But rather you can actually have this kind of like a fine pitch that you actually have a chip that is kind of bonded to the silicon, and then the connection would be there. If you're interested, definitely search, really, you can read this paper about the silicon interconnect fabric. It's one of the options. It hasn't been adopted by industry yet, but it's like very researchy but very interesting topic. This is additional slides about the SIF. So this is kind of what we traditionally do, that we have the printed circuit board, then we have our interposer, and then we have the dies, and then within the interposer, we connect them. The silicon interconnect fabric is basically saying, okay, get rid of these lag, and then you can have your chiplets directly connected through the silicon interconnect fabric. The nice thing about this is that this can then grows infinitely, because interposer, you need to kind of like interposer size cannot like increase from some specific size. You need to then find like have two separate interposer and then somehow connect them. But with this, since this is actually your substrate, you can just have as big as of a substrate as you want. Some numbers, the difference between the size of the pitch, the spacing between them, so you can actually, because of that, you have finer pitch, you can make this much closer to each other, which means that the distance between the chiplets are smaller. As a result, the communication is faster, right? Because it has to cover a smaller distance. There are really interesting things that can be done with silicon interconnect fabric. And then we actually talked about this in the Q&A of like how do we actually go from a smaller system to a bigger system. There's actually this idea of, remember I told you that we can have an NOC, you can also have an NOIF, like a network on interconnect fabric, that you can actually have like, you know, a mechanism where you can then talk to nearby devices and then far away devices using different technologies such as photonics and integrated photonics and so on. So there are lots of research in this domain actually. As I said, these are the main jobs are for like if you want to work on like pure hardware computer architecture, most of these companies are looking at these things these days. So you're gonna see something like this. Yeah, there's also standards for how to connect the chiplets. There's this standard called UCIe. Think about it as similar like a PCIe kind of standards. All right, any questions, final questions about chiplets? All right, so let me talk about the security as well, as someone asked. So what do you think? Was the chiplets gonna improve the security or decrease the security, or could be both? Yeah,
I'm gonna guess decrease security,
okay, why?
because you have a lot more like individual components.
Uh-huh.
By outside sources.
So you have the supply chain security issue that what used to be like one company that like building all of these is now you're buying it from the random places, and that could cause an issue. Sure, that's a good one.
Maybe you have like more shared resources across like all your chiplets, so could you can exploit there.
Yeah, because there might be now more outside communication between the components, right? So what used to be internal that couldn't be probed now is external, so it can be probed easier.
I feel like there might be some new side channels, especially from the length of the interconnects,
Mhm.
like EMI from that.
Yeah. So kind of a follow-up to that is a more side channel, like physical side channels, basically. Anything else? Any good things that can happen? Yeah.
If you're splitting into smaller components, you have maybe like one smaller custom component.
Yeah. So you can have like a more dedicated security components into the system. That's actually exactly what we're working on.
For like detecting maybe certain kinds of attacks, if like the functionalities are more isolated, you can kind of.
Yeah, you can have more dedicated, and then you can verify them easily, because now things are even tested, or you could verify them easily because there are smaller systems to verify, right? So verification could be simpler. Anything else? You can also, for the same reason that you guys said, they can also monitor things easily, right? So you can have dedicated, like trusted entity within your substrate, for example. So I'm going to give you like two things that we are working on. We are working on like how to use it to enhance security. Of course, all of those things that you said for, oh, this actually creates new challenges is absolutely true. In my group, we are actually looking at like specifically two things that we can use in order to improve the security of chiplets. One is how we can actually use this idea that we have a bunch of chiplets to improve the hardware security. And the second thing is that how we can actually make the monitoring more effective, because now we have smaller chiplets as we just discussed. Okay. So why we are looking at this? Because essentially, the interesting thing is that, as I said, there's like a tremendous opportunity for computer architecture to be rethink. You can also rethink many of the security problems, and you have seen in this course that these security problems are many, unfortunately. So maybe now is a good time to go back and say, okay, can I actually do something about side channel attacks? Can I do something about Spectre type meltdown type attacks? Okay. And then there is a huge interest in building chiplets and securing chiplets through the CHIPS Act, which is a multi-billion-dollar investment by the U.S. government, and it actually fueled originally by the fact that during COVID the supply chain was kind of broken, and then if you remember, like buying chips was very hard, and then they realized that like for example, people cannot manufacture cars because there wasn't chips. People couldn't many foundries and companies were like not working well because there wasn't chips. And now think about this as like a national security problem, right? These days, it's not about like, oh, can we bring water or electricity? Is that think about that if we cannot have computers or if we don't have internet, it's also a disaster for a country, right? And then unfortunately, what used to be like, recently, like in the recent numbers, is that only 18% of the chips is manufactured within the US. The rest of it is actually outsourced. And mainly is outsourced from Taiwan, which is also a very, very challenging place because if China invades Taiwan, then essentially it's gone, right? So there is a huge, huge security risk about this, and US is like very, very worried. That's why now at TSMC, they paid actually millions and millions of dollars, and now TSMC is building a huge facility in Arizona. Intel is also building one. So actually, next generation of your Apple chips is going to be manufactured in Arizona, not in Taiwan anymore. So there's actually a very interest, there's a lot of interest in reshoring, they call, of building chips within the US because of this. But then the problem is that one of them is just like making sure that we have enough chips if need be. Like, for example, if there is a war going on, we can still build chips. And the second thing is that if someone is building these chips, if someone is building these chips in some untrusted factory or foundry, they can actually manipulate those chips, and they send us the chip, but the chip is not doing what it's supposed to do. Okay, this is actually called a Trojan, and Trojan is actually very, very active area of it has been an active area of research in the past, but with the chiplets is actually growing. So what is a Trojan? I'm just showing you a very simple example of a hardware Trojan. Is a Trojan similar to a software Trojan? A hardware Trojan is that, think about you have like an adder. Think about that this doesn't exist. And then you have like a gate like this. For those of you who don't know, is there anyone who doesn't know what this, like, have never seen logic gates in their life? Okay, we're good. But maybe like a long time ago. But anyway, so this is like an XOR and an AND and an OR, it doesn't matter. But like if this doesn't exist, this is supposed to be like a sum. Like you just have to just add things, okay? So it has like three inputs, like A, B, and C. Like A and B is your input and C is your carry. It basically creates your sum and the problems, okay? And then this can be like then a bunch of this is just one bit, and of course you can add them together, create an adder, and then by adder you create a multiplier, and so on and so forth, right? So for example, if I want to do a matrix multiplication, eventually this is like what you really build, right? And hundreds and thousands of this becomes a matrix multiplier. So here's what the designer in, let's say, country X and Y can do. So you send it. This may need, this is supposed to go to, let's say, an F-35 fighter jets that's supposed to like find the objects and shoot the objects. But then what they do is that they add this tiny little gate here, okay? And then they add this also tiny little trigger, this input to it. And since this is one in billions of transistors, it's not something that you can say, oh, I see this gate, so I'm not going to use it, right? There are billions of this, and there's like literally just one of that. So how does it work? So consider like a scenario where the trigger is 0. your input is 1 0 0, you get 1 and 0, it works well. But the moment that trigger becomes 1, then this P is becoming 1. Okay, so you actually can flip bits at will the moment that you kind of cause this trigger. Okay, and and now think about this bit similar to all the things that we discussed in this class. Think about row hammer attacks. Now I have direct control over it. I don't need to do row hammer or any of that. The moment I decide the trigger can be 1, I can flip bits and I can do a lot of things. It can actually propagate all the way to your software, right? And again, if this is your object detection, maybe I decide that your object detection does not detect my objects, right? Or maybe I decide that you need to shoot a missile to something that you shouldn't, right? So there are like lots of things that the attacker can do. And this is actually, believe it or not, it's actually happened in missile detection systems for Syria against Israel. And mysteriously, it doesn't work at some point. But yeah, so generally, this is a huge problem for designing hardware. Why it happens? Because when we're sending the design to be manufactured, we send this thing called GDS2, which is kind of like a sequence of just basic gates, okay, just a bunch of transistors. But the designer can actually go and modify that and then add this little gates here and there, and they build that and ship back to you the chip. There's like literally like a needle in this haystack kind of problem, right? You cannot like find one tiny gate in billions of gates. So detecting this is an issue. Okay, so how do we solve this? There are actually lots of solutions, but the one that we are looking at is looking at this as the notion of tripletization. So how do we actually do this? So think about the same problem that we have. But this time, let's say that I somehow obfuscate the connection between the gates. Okay, maybe I can just make this known, and then later I'm going to show you how do I obfuscate the connections. But let's say I actually just make this known to an attacker. Okay, so if you actually look into this, you will see that if the attacker wants to add, remember that the thing was adding here, right? So the attacker needs to identify this gate so that they can add their logic here, right? But then if you look at this kind of obfuscated design, you see that I'm showing it this way, but if I just shuffle this around, there's no difference between V and W, right? So the attacker needs to basically randomly select between these two gates to have their trigger logic, right? So 50%. So immediately from 100% success rate, you're reducing it to 50% success rate for the attacker, because the attacker needs to know where they need to add their logic, right? This is what we call a design obfuscation. How do we actually obfuscate this design? We use this idea called split manufacturing. So the way transistors are designed are layer by layer. So you have your substrate, you design your gates and transistors within the substrate. So this is your like a CMOS transistors, or you have like, your gates here and then the three terminals. But in order to connect these transistors, you have layers of metal. So usually you go 7 or 9 layers of metal that connects them, okay? So in order to do this split manufacturing, you can actually split from some metal layer. So for example, you can say that, okay, up to metal layer 3 is designed in one manufacturing company. That manufacturing company will never give them information of what happens from layer 4 and above, okay? So when we are sending the design to be manufactured to manufacturing facility A, we're going to tell them that, okay, I need these many transistors, and here's their connection from metal layer 1 to 3. There are so many other metal layer connections, but we're not going to tell them what they are, okay? So this is actually equivalent of this, okay? So they know the gates, they know some connections, but they don't know the other connections. Okay, so we are obfuscating it this way. This is usually we call like a bottom layer and a top layer. So where we actually connect the rest, we make this connection ourselves in some trusted facility. Why do I want to send this and then why can't I do this? Because this is just some metal layers being connected to each other, very simple. I can actually do it in not very sophisticated facility. This part, building these transistors requires very sophisticated facility. So I send this to TSMC, I do this inside, I don't know, like somewhere in the middle of nowhere, in US, right? So I can do that. So usually this is the bottom layer is called front end of line or FUL. This is called back end of line or BUL. Okay, so I'll let the FUL to build on an untrusted facility and FUL where we want. And then as I said, the key assumption here is that the top tier is secure. So this way we can make sure that essentially if I remove this connection and this connection, then the adversary basically the success rate is still not zero, but this is like becomes a random decision. And if I have enough of this, then the success rate of the attacker drastically reduce. Okay, how do I actually measure that? There is this notion that's actually established notion called case security. The idea of case security is that if I can map this design into a graph, then I can measure the similarity of full design and obfuscated design and measure the number of gates that has equivalent. So for example, in this case, if I like 2 and 4, I cannot distinguish between 2 and 4. So these are in the obfuscated design is similar. So there's like the K parameter in this case is 2. For example, let's say if I have another design that has 3 AND gates and they're all connected to this one, and then I obfuscate all the connection, then I have 3 gates that are similar to each other. So we can actually measure this. So for example, from this, I can create a colored graph with edges. So like 1, 2, 3, 4, 5. The colors could be like same gate. So for example, in this case, red is like, yellow is like an OR and so on and so forth. And then I can actually measure things like this. So for example, let's say I have a graph G and a graph H. They are the same. I just obfuscate some of the connections. And then they're like U and X are the same type, V and W is the same type, and Y is the same type. Okay. So if I want to measure the case security, I can see that, for example, I can exactly say which one is 1 and 3. So U and X and 1 and 3. But I don't know which one is which, right? Because there's no connection between them. So we can say that gate number 1 and number 3 are too secure because essentially they can be used interchangeably, right? If I look at gate number 5, I see that there's only one gate that can be mapped to this, and that is 5. So 5 is 1 secure. So the adversary can pinpoint 5 with 100% accuracy. And then I can repeat this, right? So I can do it for 2 and 4 and so on and so forth. Case security measure basically says that what is the minimum, right? So for example, in this case, my design is 1 secure, which means that the adversary, if they want, they can add logic before or after 5. So you want to have a design that is like maybe 3 secure, 4 secure, whatever, right? So you want to design it such that at least for every single gate, there are multiple other gates that the adversary will be confused with. And once you do that, then you're essentially reducing the accuracy of the attacker to some random guessing. And then if you have enough of that, if the attacker needs to make 100 guesses, the probability will be so small. So you have a fairly secure system. Okay. So what is the problem with this case security on this split manufacturing? The problem with this split manufacturing is, first of all, you're going to have performance costs because now you're kind of like need to force the system to have some dummy connections in order to achieve the type of case security that you want. You need to kind of obfuscate some layers, or you need to lift the the connection between the layers to higher levels so that you can actually obfuscate them. And by the way, if you know about transistors, lower metals are faster connection, higher metals are slower. So you want to actually for for time critical communication, you want to map it to a lower level metals. Just mainly because the technology you use is more dense metals. Is also obviously it's less distance. So, but if I want to have, for example, if you really need to obfuscate this connection, that means that now I need to lift this, which means that I cannot use the like metal layer 1 to 3. I need to put it at 4 or 5 because that's where the obfuscation happens, right? But then if the latency between these two is very important for me, I'm gonna have some performance degradation, right? So that's kind of the trade-off that I'm facing. So our solution is that instead of just having a vertical splitting, let's also have a horizontal splitting, okay? So now that you are saying that, okay, we have chiplets, let's actually build chiplets this way. Let's flip this, okay? So FUL is here. Now what I'm saying is that put the two transistors in one chiplet and then put the other transistors in the other chiplet. And then also do the split manufacturing of the vertical lines. So how would that help? Essentially, this means that any given point, the adversary either sees this or this or this. Okay, so I make sure that these designs are isolated and separate from each other and nobody sees all the three parts. So essentially, not only I don't share the graph, I only share them half of the graph or partial graph. So if I go back here, essentially I no longer share this, maybe I just share them U and V. And then this is one chiplet and the other chiplet is maybe W, Y, and X or something like that. This may not be the most secure, but you get the idea, right? So I put it into two different chiplets. Okay? So with this, I can then design a graph modeling of, so this would be basically the kind of the pipeline that I have a design, I have a netlist, I build a bunch of chiplets, I send it to untrusted fab, I'm gonna get my chiplets, then I'm gonna combine them in some trusted bonding facility that can actually, the combination would be done by someone that's trusted. So this would be what you get, right? So this used to be the design that you were trying to apply your case security. This is what you're going to get after the triplet security. So you're going to have some internal connection within each chiplet. That's what the adversary will see. But these things the adversary will not see because these are going to happen later. We also then start thinking about, okay, how do we apply case security to this? We saw that case security generally doesn't understand the difference between disconnection and disconnection. So we come up with some other metrics called intersimilarity and intrasimilarity. That for the interest of time, I'm not going to go through the details of this. But generally, the idea is that you want to make these chiplets as similar as possible to each other. Because if I can make them as similar to each other, then the adversary cannot distinguish the nodes within each one. Okay? So that's kind of like the basic idea of this intersimilarity and intrasimilarity. I'll let you guys take a look at it if you want to. And then I can then have the notion of level of trust. That essentially this level of trust can tell me how much I'm like prioritizing my performance and making sure that the communication is as fast as possible and the design is as performant as possible versus how much I'm trying to make these chiplets and make these nodes similar to each other. And this is like a designer's option to decide where in this design space they want to land. Okay, so this is kind of like make sure that the system is like a balance between performance and security. We actually kind of show it like a number of chiplets and number of layers and level of trust. And you can actually then kind of like with a given number, you can kind of come up with design. So for example, like for a particular level of trust, you can say that, okay, my design needs to be like 4 chiplets and I need to like, have the cut metal layer cut of 4. So I need to cut this at 4, and I have to have for example, 4 chiplets to divide this. This is how I'm going to build this system. So this is for a given system, for example. We look at different circuits, and for each one, you need to basically run this. Of course, there's like a lot of complexity that you need to be worried about as your kind of like, the design size grows, and then the number of chiplets grows. There are overhead that comes with this. So this is not free in terms of overhead. So you're going to have power overhead, you're going to have area overhead, you're going to have delay overhead, you're going to have wire length overhead, because now you need to have more wires. But it gives you a more security. So it's kind of like, you pay for extra things, but you achieve more security in the system. Okay? You can actually then think about how you chipletize your design. So all those questions that I gave you for the computer architecture aspect of things, you can then plug in this security aspects to it as well. So when I'm designing and thinking about designing my chiplets, I can also think about similarity as another factor, or I can think about wire length as another factor, or I can think about key security as another factor. And then you can then start jointly optimizing this thing. So there are interesting observation and directions in this scenario. One final thing I want to say before I let you guys go is the idea of what we call security helper chiplets. Okay, so the idea is, bless you. The idea is that now I'm like going from like a one monolithic design to smaller chiplets. I can have dedicated chiplets that does security services for me, and we call them security helper chiplets. Okay, so this is what you can imagine that could happen. So this was kind of like the design of a chip yard or a SoC base that I showed you at the beginning of this lecture. But usually you can have like a very tightly coupled, components. This could be an accelerator, it could be a security component, or you can have like an MMIO base that sits in the bus. But with chiplets, you can actually have now 2 other options. You can actually put some security features inside your substrate. There are actually technologies that even should help you to put active logic in your substrate. So for example, all the communications that goes from this chiplet to that chiplet can be tapped in and monitored. The second thing that you can have is that you can have like dedicated security chiplets that kind of spread around your big design and provide security services to their nearby chiplets. So for example, all of these chiplets, not only they send each other data, they also send data to this security chiplets. So what can you do with this? There are various things that you can do with this. So you can actually like have it for cryptography, you can use it for malware detection, you can do it for memory safety, you can do it for side channel detection, and so on and so forth. How do you actually design this? We actually look into that. Do we want to, for example, have like a centralized design? Do we want to have some form of a hybrid design that we have a little bit of security services for each chip, and then they also talk to like some form of a centralized one? And this is kind of the traditional model that we had in the past, that all your security services work within each SoC. So you can actually have now a range of solutions if you want to. And some of the services can be here, some of the services can be here, and then some of them can be distributed across the system. So there's lots of interesting opportunities for like a hardware security modules that you can add to your system. Okay. And you can also have, so we call this like security helper chiplet, a utility chiplet. And then this utility chiplet does not need to be just security. It could be also other aspects of the system. So remember I told you that in order to connect these guys to each other, I need like a power, I need like maybe some form of a electrical to photonics conversion and all that. So I need some chips for that, right? I can actually then put my security services into that chips as well. So I can have like a unified utility chiplet that not only helps me with power consumption and clock distribution, but also helps me with security. So that could be like a future design of these systems. Okay? Any final questions? Yeah, this is what we think is going to happen in the next 5 to 10 years. So thank you guys. I'll see you next Wednesday.